In this video, we will talk about scalar and vector fields. In physics, we study phenomena that usually varies either in space or time. So the concept of scalar and vector fields allows us to translate the physical quantities into the language of mathematics. Then we can mathematically manipulate them and predict how the physical systems behave with space and time. So let's start with the scalars. Scalars can be defined as quantities having magnitude only. Some examples for scalars are mass, time, and temperature. If you can assign a scalar value to every point in space, then we call that a scalar field. Examples for scalar fields could be density of a gas, pressure in a liquid, or electrostatic potential. So if you have a world map indicating the temperature at each and every point on the map using different colors, this is a representation of a scalar field. Scalar fields can be represented in different other ways. So, for example, a 2D or 3D map representing the intensity of the scalar value using different colors is all one representation. Or you can have contour maps which connects points of equal value of the scalar field and you get a map like this. So this is a representation of the height in a region from the sea level. And you can have relief maps where it's a two-dimensional representation of the three-dimensional height from the sea level. And then also you can represent the scalar field using an equation, using a mathematical equation like this. If you have a line or a surface where the scalar value is a constant throughout that surface or line, it is called a level surface. Examples for level surfaces could be equipotential surfaces where you draw a line connecting the points with the equal potential, and the contour lines, that is again lines joining the equal potential points, and isobars. So they are connecting the lines where there is constant pressure. These are some examples for level surfaces. Now let's get to the topic of vectors. So vectors can be defined as quantities having both the magnitude and a direction. Examples for vectors could be displacement, velocity, acceleration, force, and moment. And in a certain region with time, if we can assign a vector to each and every point in space with time, that is called a vector field. So examples for vector fields could be electric field, magnetic field, displacement field, and a fluid flow. It could be liquid or gas, which can also be called a velocity field. This is an example of a representation of a vector field. So you can see the magnitude of the vector is represented by the length of an arrow, and the direction of that particular vector is represented by the direction of that arrow. So we can actually use an arrow to represent a vector. The magnitude of that vector corresponds to the magnitude of the value, and the direction this arrow points is the direction of that vector. So in a particular coordinate system, if we have a particular vector, we can decompose these vectors into different components along the different directions. We can decompose this vector into parts. So vectors can be represented geometrically as an arrow, or we can represent it as algebraically using some we usually draw an arrow on top of the letter representing the vector. Sometimes you could be using bold letters to show that it is a vector. Uh, Sometimes you use this hat notation to denote what is called a unit vector. So unit vector, it's a vector with magnitude 1. So the magnitude of the unit vector is 1 and its direction is the corresponding direction of this vector. So usually unit vectors are denoted with this hat notation and the normal vectors are denoted with an arrow on top of the letter. So we can both algebraically and geometrically represent the vectors, geometrically using arrows, and we can draw vector fields like this. So this is an example of a fluid flow.